Hello, this is going to be the fourth tutorial. I'm going to share my screen here. You should be seeing the tutorial. And with this tutorial, we have three identical bricks, and we're going to draw a circle around these two bricks here and call them System A. And this third brick will be System B. And we see that because they're identical bricks, System A has twice the mass as System B. We're first asked to compare the net force, the total force, magnitude and direction on System A to that on System B. And this is kind of a trick question, because if we read up above, we're told that these identical bricks are pushed across the table at constant speed in a straight line. And so that means that the acceleration of A is equal to the acceleration of System B is equal to 0. Now, by Newton's second law, F net equals ma. It doesn't matter what the m is. If A is 0, we have net force on A equal the net force on B, which is equal to 0. So the free body diagram for A and the free body diagram for B have to scream balance. They have to scream 0. Now we're asked to draw those free body diagrams, and I encouraged you in class to always draw the free body diagram of the simplest object first, the thing that's touching the fewest other things. And that's going to be System B. So the first force we put on that diagram, of course, is the gravitational force, Earth pulling on B. Then we ask, are there any magnets? No. So what touches B? Well, there's the push by A, a normal force. And I know that that's a normal force and not a friction force, because I could grease down the surface between A and B, and it's not going to change the problem one bit. I also know that the table pushes on B, and it pushes with a normal force up and a friction force. Now, we know there has to be a friction force, because otherwise that block B would be accelerating, speeding up to the right. And so that's going to be a friction force by the table on B. Now I'm sure that I've got the right free body diagram because I followed the recipe. I started with the weight force, I looked for any magnetic forces, and then I made a list of the things that touch B. Well, A touches B, and I took care of that, and the table touches B, and I took care of that. So now let's draw a free body diagram for A. Well, A has twice the mass. It's 2 bricks, so it's going to have twice the weight. Again, there's no magnets, so we don't have to worry about that. And then I ask, what touches A? Well, B touches A, and the table touches A, and the hand touches A. Well, let's take the contribution from B. If A is pushing on B to the right, B has to push back just as hard on A. And I'm going to put a tick mark here and a tick mark there to indicate that those are third law companion forces. If I look at the force exerted by the table, there's a normal force by the table up, and then there's a friction force. Now, the friction force we found in lecture, kinetic friction, because there's scraping going on, by the table on A is going to be the coefficient of kinetic friction times the normal force by the table on A. These indices always have to be the same. Now, you see that since the normal force by the table on A is twice as big as the normal force by the table on B, the friction on A has to be twice as big as it is on A as it is on B. And now I'm just going to make my dot bigger so that I can put those two forces side by side. Now the last object to touch A is the hand, and it has to push with a force big enough to balance these two together. And so I'm going to call that a normal force by the hand on A. Okay. Is the magnitude of the force exerted on system A by system B greater than, less than, or equal to the magnitude of the force exerted on system B by system A? So what they're asking on is NBA and NAB. And we're looking at the magnitudes. And those have to be equal by Newton's third law. Okay. Now, if I were comparing the forces instead of the magnitudes of the forces, I would write it as the normal by A on B is equal to the normal by B on A with a minus sign. That minus sign means that they are in opposite directions. But here I'm just saying that the magnitudes are the same. The directions are opposite. Would your answer change if the hand were pushing system B to the left instead of pushing A to the right? And the answer is the normal by B on A is always going to be equal to the normal by A on B by third law. It doesn't matter which way we're pushing that, but the magnitude would change. The normal force here, the normal force between the two blocks had to balance the friction on B. If we were pushing the other way, it would have to balance the friction on A. So the magnitude would change from the friction by the table on B to the friction by the table on A. Magnitude. Okay, those are vectors, of course. Identify all the Newton's third law action-reaction force pairs in your diagrams by placing tick marks there. And we did that. And these were same flavor. Flavor was spelled with an O. By that I mean both are normal forces. With indices reversed. Okay, instead of A on B, it's B on A. And my my answers are consistent because they're right. So now if we go to the next page, we know that we have to rank these forces, And it's just the horizontal forces that we're asked to rank. So we know that these two are equal by Newton's second law. We know that this is equal to that by Newton's third law. Okay, so if I make a list here from, I'll call this largest up here and smallest down here, I'm going to put these in the middle here. So this is by the third law, and this is by the second law with zero acceleration. Now, we know that the friction by the table on A is equal to twice the friction by the table on B, so that's got to be bigger than those three. And we also know that the normal force by the hand on A is equal to the normal by B on A plus the friction by the table on A. So this would be the largest, and these will be the smallest. Did we apply Newton's second law in comparing the magnitudes? Yes, we did it here on the free body diagram for B, and we did it here on the free body diagram for A. So did we apply Newton's third law? Yes, we said that the normal by A on B was equal to the normal by B on A. So here we said that the normal by the hand on A was equal to the normal by B on A plus the table friction force on A. And I'm leaving the vector signs and the magnitude signs off. If I don't have a vector sign over the top, we'll accept that as a sloppy notation for the magnitude. And here we had the normal by A on B equals the friction by the table on B. Okay. What information besides Newton's laws did you use? And that was that the friction force, kinetic friction, was equal to the kinetic coefficient of friction times the normal force. And if I want the friction by the table on A, I need the normal force by the table on A. And that's going to equal twice mu sub k times the normal of the table on B, which is going to be twice the friction by the table on B. So in other words, the stack of two bricks, since it's got twice the normal force, will have twice the friction. Now, suppose the mass of each brick is 2.5 kilograms, and the coefficient of friction between the bricks is 0.2, and the bricks are moving at a speed of 0.5 meters per second. So if we start using that information to find the size of the forces, let's start with the weight forces. The earth on B is going to be 2.5 kilograms times 10, 9.8, call it 10 newtons for each kilogram. And that's going to be 25 newtons. The earth pulling on A is going to be twice as big. That's going to be 5 kilograms times 10 newtons for each kilogram, or 50 newtons. The normal forces, of course, the normal force by the table on A is going to balance the weight of A, and so that's going to be 50 newtons. And the normal by the table on B will be 25 newtons. Now, the friction force by the table on B is going to be the coefficient of 0.2 times the normal force, which is 25 newtons. And that's going to give me 5 newtons. Now the friction force by the table on A is going to be twice that big, or 10 newtons. And that means that these normal forces A on B and B on A are also going to be 5 newtons. Now, the normal by the hand on A, remember, was equal to the normal by B on A plus the friction by the table on A. And that's going to be equal to 5 newtons plus 10 newtons, or 15 newtons. So if I go back to my diagram, this is 25 newtons. This would be 25 newtons. This would be 5 newtons, 5 newtons. This would be 5 newtons by Newton's third law. Because this friction is double that friction, it would be 10 newtons. And to balance this free body diagram, this would be 15 newtons. This would be 50 newtons, 50 newtons. So we're done with the first 2 pages, except it asks, would we change our answers if the bricks were moving half as fast? And because the friction by the table on B and the friction by the table on A don't depend on speed, our answer would be a resounding no. Now, on page 3, we do everything over again. We do the exact same problem over again, only this time we polish the table a little bit before we start pushing. And the hand pushes with exactly the same force that it did before. But now with that polished table, so that the coefficient of friction in part 2 is less than the coefficient of friction in part 1, instead of having constant uniform motion, the systems are going to speed up. We're going to have an acceleration to the right. And because they're moving together, every time A moves to the right by an inch, B moves to the right by an inch. So that means that the acceleration of A is equal to the acceleration of B, and it is not 0. Now, because the net force is equal to the mass times the acceleration, well, the mass is going to be 2 times bigger for A. But the acceleration is the same. So that means that the net force on A is equal to twice the net force on B. Now, if I draw my free body diagrams, again, I start with the simplest system, B, and I put the weight force and the normal force, get rid of the easy ones. I've got this push by A on B, and now the friction force is smaller than it used to be. And that's because we polished the table. And you can see that this free body diagram screams to the right, as it should. Now, if we draw the free body diagram for A, again, we've got a weight force that's twice as big, a normal force that's twice as big. We have this normal by B on A, that's a third law companion to this force. And our friction force is still going to be twice as big on A as it is on B, but it's going to be smaller than it was before. And now the push by the hand is exactly the same as what it was before. That's given in the problem. And so you see that this diagram also screams to the right. Now, if I consider these statements by the student, systems A and system B are pushed by the same force as before, so they will have the same motion as in section 1. No. They accelerate. I disagree. I think they are speeding up since friction is less. So far, so good. Student 2 said something true. So now system A is pushing on system B with a greater force than system B is pushing on system A. So student 2 just gave up on Newton's third law. This is, they have to be equal. The normal by A on B has to equal the normal by B on A. And here I'm talking about the magnitudes. They're opposite in direction. So I agree with neither student. If I rank the magnitudes of all the horizontal forces that appear on the free body diagram, I get a similar answer to what I had before. I know that the normal force of A on B is equal to the normal force by B on A. I know that the normal force by the hand on A is still the biggest because it's the normal of B on A plus the friction by the table on A. I know that the friction force on B is going to be the smallest of all of them, but I can't rank the friction force by the table on A. It either goes here in my ranking or it goes here on my ranking. And I don't know because I don't know how much I polished that table. If I polished it just a little bit so that this friction force just becomes a little bit smaller than it was before, well, the friction on A, which is twice the friction on B, would be up here, greater than the normal forces by B on A and A on B. But what if I polished the table just so smooth that I, essentially made it almost frictionless? Well, then both of these friction forces would be down here below the normal forces between A and B on A. So I can't fully rank all of the forces without knowing a little bit more information. Now, we've done this several times in other tutorials. We are going to define a new system. We're going to lump all three of those bricks together. Essentially, we're going to define a system where C is equal to system A plus system B. And we want to compare the net force on C to the magnitude of the net forces on A and B. And so I know that the net force on C is equal to the mass of C times the acceleration of C. Well, that's going to equal the mass of A plus the mass of B times the acceleration of C. Well, that's just going to be equal to the net force on A plus the net force on B. So the net force on the system of A plus B is just the sum of the net forces. Now, if I draw a free body diagram for C, I only want to draw forces that are acting on C from outside the system of C. Well, the Earth is pulling with a gravitational force on C. The hand is pushing with a normal force on C. The table is pushing with a normal force on C. And I have a friction force by the table on C. Now, for each of these forces that appear on your diagram for system C, list the corresponding force or forces on your diagrams for A and B. Well, the weight of C is just equal to the weight of A plus the weight of B. And the normal by the table is just the normal by the table. The normal by the table on C is just the normal by the table on A plus the normal by the table on B. And the friction force here is just going to be the friction on A plus the friction on B. Now I can do the same thing for the normal by the hand on C. Since C is A plus B, I would have the normal by the hand on A plus the normal by the hand on B, but the hand never touches B, so that's 0. So the normal by the hand on C is just what we had on A before. Are there any forces in your diagrams for A and B that did not get on this diagram? And it's the normal by A on B and the normal by B on A. And these are internal forces that do not affect the motion of the system. We call them internal forces. If we draw a free body diagram of Greg, we don't include on that diagram a force by the liver on the spleen or the force by the spleen on the liver. It's only forces exerted by things outside of the Greg, like the floor or the earth, that affect the motion of the Greg. Now, if we look at this free body diagram for this cart, I've got a level surface that doesn't look very level, and this cart is on that surface, and we have a rope pulling on the cart. We have this normal force by the table on the cart, and we have this gravitational force, Earth on the cart. And what we can say about the motion from our free body diagram is that it has an acceleration to the right. Now, could the cart be moving to the left? Well, yes. If the cart is moving to the left with an acceleration to the right, it would be slowing down. Could it be moving to the right? Well, yeah. And if it's moving to the right, it would be speeding up. Could it be stationary? Yeah. For example, at a turnaround point, if this thing were moving to the left, slowing down, and then right at the instant where it turned around to go the other way, speeding up, right at that turnaround point, I would have 0 velocity, but I would still have an acceleration at that turnaround point. So that would be a turnaround. The key here is that the free body diagram only tells you about the acceleration. It tells you absolutely nothing about the velocity. Indeed, this whole setup could be in an elevator that was moving up at 1,000,000 miles an hour. As long as it was a constant 1,000,000 miles an hour, it wouldn't change anything in our free body diagram. And so there's just all sorts of motions that are possible. The one common thing among all the motions would be that the acceleration would have to be to the right. Okay, I hope this was helpful. I'm going to stop the share, and then I'm going to stop the recording.